Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper data structures. And in this module, we are going to talk about a different type of tree called multivariate trees, and we are going to talk about multivariate trees and 2-3 trees. So, we are going away from binary trees in this module. So, these are the people responsible for the development of this module, and now let us look at the learning objectives of this module. The learning objectives of this module is to understand the idea of multivariate trees, to discuss the concept of 2-3 trees, to discuss what is 2-3 trees, because this is the first time we are looking at balance. Okay, I did not talk it is balanced, it is actually balanced multivariate trees, and then to describe the operations on 2-3 trees, and then we are going to these are the keywords: multivariate trees, redistribute and merge. So, with this learning objectives, let us go into the multivariate trees. So, first we start with what are multivariate trees. So, these are not binary search trees obviously, because it is not binary search trees are two-way trees. Okay. Here we are talking about multivariate trees. So, they are not binary search trees, they are not necessarily binary. Of course, you can have 0, 1, 2 up to m or whatever way. So, they maintain all leaves at the same level. No, this is a little different from what we saw for binary search trees. So, they maintain all leaves at the same level, same depth, and the number of children, but the number of children can vary. And so, here in this module we are going to talk about 2-3 tree, that is each node can have 2 or 3 children, and later on in the next module we will be talking about 2-3-4 tree, where each node can have 2, 3 or 4 children. So, B tree is a special case where we can have B by 2 to B children roughly. Now, that again we will be talking about in later module. So, in this module we are going to talk about 2-3 tree. A node can have 2 or 3 children, but more importantly please note that all leaves are maintained at the same depth. So, let us go back to balanced search trees. In the previous before 4-5 modules, we had spoken about balanced search trees, but we had spoken in specifically about balanced binary search trees. Here we are not talking about binary search trees. So, 2-3 trees, each internal node, now look at the difference, we are talking about something called an internal node and an external node. So, each internal node can have 2 or 3 children, all leaves are at the same level. So, all leaves are at the same level. So, this is an example of a 2-3 tree, where you can see that all the leaves are at the same level, and if you look at the root, it has 3 children, and in the middle level the leftmost node has 2 children, the next node has 2 children, and the last node, the last sibling in the next level has 3 children. So, if you look at, we will come to that later. If you look at each node, the number of keys that are maintained there is less than the number of less than the number of children. We will come to that. So, 2-3-4 trees, we are not discussing that in this module, but just for a comparison, again is a multivariate tree, where each node can have at the most 4 children. In 2-3 tree you can have at the most 3 children, and a node can hold up to 3 values. Here a node can hold up to 2 values, in which in 2-3 tree. So, and can be perfectly balanced. So, no difference in height between the branches, all the branches will have the same weight. Requires complex nodes and links, that is one of the issues, and this is an example of a 2-3-4 tree, where you can see the number of values it holds is 3, and the number of children, maximum number of children it can have is 4. So, but we are not going to look at 2-3-4s only in the next module. Now, we are going to look more in detail at 2-3 trees. So, another way of balanced search tree. So, in this first introduction we are looking at all the balanced search trees that we are going to look at. One was 2-3, one was 2-3-4, and the next we are looking at is B tree. So, this is again a multivariate tree, where each node can have at the most m children, and a node can hold up to m-1 values. So, this is true for all the 3. 2-3 you can have maximum 3, you can the node can have hold maximum of 2 values, and 2-3-4 you can have maximum of 4 children, and the node can hold maximum of 3 values. Here you can have at most m children, and the node can hold a maximum of m-1 value, and it is a more general version of 2-3-4 tree, and commonly used in databases and file systems, Most nodes are stored in secondary storage such as hard disks. That is why the B trees is a very popular. B trees and an implementation of B trees called B plus trees is very popular method in database storage, where you know the number of the storage requirement of keys is very high, and so the search time is also high. We will go into this just to give you a feel of what is a B tree. We will go into this again in detail when we go to the module which is going to deal with B and B plus trees separately. Okay. So, up to this point we have seen there were 3 types of balanced tree, search trees, all of them are search trees. Remember what is the meaning of search trees? If you take a node, what are its children on each in each subtree is determined by some lexicographic order. We looked at in detail only about binary search trees, where we had root, left and right. In all the balanced search trees that we are going to look from now on, where we say multi-way search trees, the search tree property is satisfied, we will see how later. But then here we had 2, 3, 2, 3, 4 and B trees. So, all the 3 are multi-way balanced search trees, okay, except they are not binary, otherwise all the properties are satisfied. It is balanced, it is a search tree. Now, let us go to in detail to 2, 3 trees. So, 2, 3 trees. The features of a 2, 3 tree is each internal node. Now, here we are distinguishing between what is an internal node and what is a external node. External node means all the leaves. So, an internal node can either have 2 or 3 children, and all leaves will be at the same level. So, an example here is, this is an example of a 2, 3 tree. Okay. Details about this will go again. Now, let us look at a 2, 3 tree named for number of possible children each can hold, that is why the name 2, 3 tree. Each node is designated. Now, look here, you have different types of nodes. So, each node is designated either as a 2 node or a 3 node. You can have 2 types of node. All the leaves are at the same lowest level, and a 2 node is the same as a binary search tree node, no difference. So, remember what is a binary search tree node? You have a node, left subtree will have values lesser than the root, right subtree will have all values greater than the root. And then, so this is an example. A 3 node, this is an example of a 2 node. Now, if you look at a 3 node, we will come to a 3 node, it contains 2 data fields. Now, look at this, it is an internal node, it has got 2 data items fields. First item is lesser than the second item, and it references 3 children. The first holds value, the first child holds or subtree holds value less than the first data field. The second holds values between the first and the second data field, and the third holds values greater than the second data field. So, if you look at that here, this is what we are trying to say. So, T contains a root and 3 subtrees. Okay. So, TL, TM and TR, meaning lower value, middle value and right value, or left, middle and right. So, 3 subtrees, and if you look at the node, it has, it is a 2, 3 tree. So, TL, TM and TR are all 2, 3 trees themselves, and each of height h minus 1, okay, and all same height. The root contains 2 data items, maximum of 2 data items called S and L, search keys S and L, and each subtree TL will the key in TL will be less than S, and each key or less than each search key in TM. So, it will be less than S. Then in TM will be between in TM will be between L and S, and in okay. So, you have 3, the root contains 3, each search tree in TL will be less than S, in TM will be between S and L, and in TR will be greater than L. So, that is the idea. So, let us say example of a 2, 3 tree. So, here you have S and L values being 50 and 90, okay, and that is a 3 node because it has 2 values and 3 children. So, that is the first thing you should understand. And then on the left hand side you have a 2 node, which means it will have only 1 value and 2 children, and in the middle also you have a 2 node, it has 1 value and 2 children, and on the right hand side you have a 3 node, it has 2 values and 3 children. So, that is the first thing we have to understand. Now, if you look at the search key values, now first let us look at the 2 node subtree at rooted at 20. All the elements in that subtree will be less than 50. Okay. All the elements in the node rooted at 70 will be between 50 and 90. Okay. All the keys of the subtree rooted at that to 3 node containing the data values 120 and 150 will have a value greater than 90. Okay. So, now that is the idea. Now, let us take the 2 node, this is true, this is a recursive definition. So, let us take the 2 node 20, this is similar to a binary search tree. So, the node in the left subtree will be less than 20 and the right subtree will be greater than 20, except that that has a that itself is a external node. So, if you look at the bottom, they are all external nodes, they do not have any children, but have values, and those values are follow the same property. So, that subtree has values greater than 20. Now, if you take 70, that again is a 2 node, left is less than 70, right is greater than 70. If you take the 3 node containing 120 and 150 as S and L, then you will see that all the nodes, the search keys on the left subtree is less than 120, in the middle subtree is between 120 and 150, and in the right subtree is greater than 150. So, search key is greater than 150, but less than in this particular part is the search key is greater than 120, but less than 150, and here the search key is greater than 150, here the search key is less than 120. So, this is it. So, each non-leaf has 2 or 3 children and all leaves are at the same level. This is a typical example of a 2-3 tree. Now, the efficiency of a 2-3 tree, insertion deletion can be defined so that the 2-3 tree remains balanced and its other properties are maintained. In particular, a 2-3 tree with n nodes never has a height greater than log 2 of n plus 1, and same as the minimum height of a binary tree with n trees, n nodes. So, this is a very good issue. Searching an item in a 2-3 tree is never worse than of the order of log n, regardless of the insertion and deletions that were done previously. So, whatever may be the situation, the searching of an item in a 2-3 tree never exceeds, worst case itself never exceeds of the order of the time complexity never exceeds of the order of log n. Traversing a 2-3 is similar to the in order traversal, no difference. Now, let us take look at insertion. So, it has to maintain the property of a 2-3 tree, it has to be balanced, it is a search tree. So, all those has to be done. So, let us look at the basic idea. So, basic idea is find a leaf that where a new item x should be inserted and insert it. Okay. If a leaf now contains only 2 items, as initially it was contained 1 item, you always insert at the leaf, that you have to know. So, find where you have to insert depending on the search property, and if you find that after insertion it contains only 2 items, you have to do nothing else, you have just done. If the leaf now contains 3 items, let us say x, y and z, then you are violating the 2-3 property, because each node can contain only 2 values, here you have got 3 values. So, you have to do some operations. Replace the leaf by 2 new nodes. Okay. So, instead of having that leaf, you replace the leaf by 2 new nodes n1 and n2, with the smallest of x, y and z going into the n1 and the larger going into n2, and the middle value going up to the leaf's parent as a parent node p. Okay. Now, we will understand this further as we go along. So, just note I have 3 items x, y and z. Now, I take the leaf node and introduced replace the leaf node by 2 new nodes. Instead of 1 leaf node, I am having 2 nodes, and in n1 whichever is smaller, let us assume x, y, z, x is smaller than y, y is smaller than z, then let the smaller one x go into n1, the larger one, that is z, going to n2, and the middle value will go up to the parent of this original leaf as a value. Now, there if you only had 1 child previously, this addition will not cause a violation. Now, suppose that had 2 children, then there is a violation, again you have to do this split. Now, actually what you have done is you split the leaf node, instead of it having 3 values, you are splitting it to having 2, 1, 2, 1, 1, 1. So, make n1 and n2 children of the parent p. So, if parent p now contains 2 items, that is what I said, and now has 3 children has 3 children, you are done. But if the parent now contains 3 items and 4 children, then you have to proceed again to step 3 and do the same operation again. P's leftmost children are attached to p n1 and the 2 rightmost children are attached to N2, and repeat step 3 to 5 until arriving at a parent which contains only 2 data items. So, what you are doing is you are moving it up the tree. What are you moving up the tree? So, you go to the leaf, you find you have violated the rule. That means, instead of having 3 children, you are having 4 children. Suppose you had only 2 data items after insertion, no problem. If you had 3 data items, not allowed. So, you split it and then create a new parent, and if that parent can be attached to the previous parent, no problem. Otherwise, again violation, split it again, go back and keep doing this till you have reached a node that contains only 2 items. Note that the root itself can be split. So, let us take an example to understand this better. Now, let us assume that we are inserting 36. Okay. So, when you insert 36, what happens? 30 it goes into, remember the insertion. So, first let us look at that. All nodes to the left of 30 are lesser than 30, between 30 and 39 comes in the middle, and I will just call it as left, middle and right. So, after 39 comes into the right. Now, 36 has to be inserted between 30 39, which means it has to go into the middle node. When it goes into the middle tree, what happens? We will see this as we go along. So, now it has 3 values. Now, let us assume that we want to insert 37. Now, if you want to insert 37, 37 has been inserted. Now, you want to insert 36, that is what we saw before. So, 36 is inserted. Now, if you look at this here, this 36, 37, 38 okay, is overcrowded. So, you have to divide that leaf and move the middle value up to the parent. So, that is what we have to do, it is overcrowded there. Okay. So, now you are still inserting 36. Now, when you insert 36, divide the overcrowded row, divide the overcrowded node and move the middle value to the parent and attach this the children to the smallest and the largest. So, the result will be as shown there. So, let us just go up here. So, you have 36 there. So, what you have to do is you have to split 36 and 38, and what happens? Please note here, first on the left hand side in A, what has happened is you have inserted in the leaf and you have found that you have violated the condition. So, what you do, you split it up as 36, 37, 38, 36 you put as a leaf, 38 you put as a leaf, 37 you move to the parent. The parent originally contained 30 and 39. So, you move it as having 30, 37 and 39. Now, what happens? 30, 37, 39, that node has become overcrowded. So, again you have to split that, we will see that. So, now what happens? You are going to, please note here, you have 30, 37, 39, you split it as 30 on one side, 39 on one side and 37 to the root as in the 50. So, here you have the 36 attached 30. So, you have 37 moving up there. Now, that has no violation of property, because it already had only one child, one value, 2 children. Now, you are making it having 2 children and 2 values and 3 children, which is fine. So, now look at what has happened. 36 has been attached to 30, 38 has been attached to 39, and this is the overall scenario where we have 10, 20, 36, 38, 40, 60, 8 and so on. So, now you had 2 levels of splitting. One, you split the leaf and then you split the parent till you reach the root, may be the root or may not be the root, but some node where you had only one child. So, you were able to accommodate by 37. So, that is the insertion of 36 into this 2, 3 tree. Now, after this, now this is the original tree. Now, after this I have inserted 35. So, when I inserted 35, nothing happens because already it had only one child. Then I insert 34 and then I insert 33. So, after this you get this whole tree, but there has some of the nodes have become 3 child, but otherwise no difference. If you look here, all the nodes have either 2 values or 1 value, or 2 children or 3 children. So, to insert an item I into a 2 tree 3 tree, first locate the leaf at which the search for I should terminate, then insert the new item into the leaf. If the leaf now contains only 2 values, 2 items, then you are done. If the leaf contains 3 items, you must split it. So, basically we are doing a splitting operation as we seen from the example. So, the first operation is how to split this leaf, that is what we are going to answer now. So, the first question is, you have SML, that is you have got 3 now, and I mean after the insertion you have got SML, and this SML is to the left of the parent and the parent has only 2 children. Then what you do, you just take S on one side, L on one side, and the previous whatever child it has, it remains there, and M goes up, no violation of property, done. The next case you have as a right child, here also no problem because the original parent had only 2 children or 1 value, now you have got it to have 2 values and 3 children, fine, M moves, but M is placed to the right of P, that is the only difference. So, this is the splitting the leaf A and B cases. Now, if it is more than this, that is if you get a split and you have to, the parent has only 2 values, we saw from the example what had to be done. The deletion algorithm strategy for a 2-3 tree is the inverse of the insertion strategy. In insertion we had to do a splitting, in the deletion we will have to do a merging, we will see that. So, 2-3 spreads insertion throughout the tree by splitting nodes when they become too full. The spreads deletion throughout the tree by merging nodes when they become too empty. So, that is the opposite of insertion. So, we will see how this is done. So, now let us assume that we want to delete 70. Okay. So, suppose we want to swap the in-order successor. So, we have swapped the in-order successor and delete the value from the leaf. So, we have deleted the value from the leaves and then you merge by deleting the empty leaf and moving the 80 down. So, this is what we have done. This is the deleting of 70 and finally, this is the tree that we will get after the deletion operation. Now, suppose we want to delete 100, delete value from the node from the leaf. So, you delete 100 from the leaf, it does not work. So, you redistribute it such that you get what you want. So, there are deleting from a 2-3 tree has 2 operations, that is you have SL and you have a parent with 1 child and you have an empty right subtree. Then you redistribute it such that S, L and P, a small rotate, that is a redistribution, or you have SL, have SL and a empty. Then what you do, you move it up and make SL merge SL. So, you have redistribute and merge as 2 operations of deleting from a 2-3 tree. Internal node, this is as far as external node is concerned. In internal node, for example, look at this, you have a parent and you have SL and you have a right with 1 child. Now, what happens, you have deleted the child, so that becomes empty. So, you redistribute it, make L the root, rotate it such that L becomes a root, S has now 2 children A B, L has P and P has 2 children C, the original child from the left, and then C D. Similarly, you can do a merge, this is internal nodes, leaf we saw in the previous slide. So, you have here S, A B, L and an empty thing. So, what you do is you merge it such that SL, the L comes down, again it is a sort of rotation only, but you have to rearrange the nodes appropriately. So, if it has an empty root, that can happen. If that happens, you just delete the root, but the height will reduce by 1. So, that is the deleting the root. So, you had 3 cases of delete essentially, 1 the leaf, then 1 the internal node and 1 the root. So, when you do the deletion at the leaves, what you are doing is you are redistributing and merging. When you are doing internal node also, you are redistributing and merging with appropriate rotations. When you are deleting the root, you are essentially removing a empty root and decreasing the height. So, in this particular 2-3 tree, we saw some interesting operations. Actually 2-3-4 tree is extended to B tree. So, this is easier to understand. So, that is what we have done here. So, what we did here was in this 2-3 tree, next we will go to 2-3-4 tree, which is a little more different. Here what we did was, we checked whether the leaf where we do an insertion has more than 3 values or 3 values, there are no children. So, 2 values, if you do an insertion 2 values, no problem. If you do an insertion and you get 3 values, then you have to split. Now, that is easy. When you do the split, you have one of the child, I mean when you get 3, you take you split it into 1 left, 1 right, the middle goes up. When you go up, that parent, if originally had only 1, now it becomes 2 values, no problem. If it gets 3 values, that has to be split, and you keep doing this till you reach the node where you have only one value and only 2 values after the insertion of because of the split you have insertions. So, in fact, you have a series of insertions that you do. In the deletion, what did you do? The opposite. There we had two crowded nodes, here we have empty nodes. So, what you do? You do merging, but not only merging, you may have to redistribute in such a way that the appropriate search properties are maintained and the balance is maintained. So, you do a proper redistribution. So, in deletion you had 3 cases, you had leaf, at the leaf if you delete, what happens, how do you merge? Internal nodes, if you again both are merge and redistribute, how do you merge and redistribute? And at a root, what you do? At a root you do a deletion and decrease the height. Okay. So, in this particular module we had explained the idea of multivariate trees. We discussed the concept of 2-3 trees, what does it mean? It different from what we have seen up to the previous modules because of the following. One was you allowed more than 2 children, okay. The similarity was it was supposed to be a search tree, it is balanced, that way that remains the same, but the difference is you could have more than 2 children and you had a concept of all the leaves all being at the same level, that is what a very important property, and you had keys values at the nodes which was 1 less than the actual the number of children allowed, and we had the concept of splitting and merging so that the properties was maintained and some redistribution so that the balancing was maintained and the search properties maintained. So, we describe operations on 2-3 trees, search, basically we discussed insertion and deletion. When the property of 2-3 trees becomes violated, what happens? One, it became overfull, one it could become empty. So, in the next module we will be talking about another type of multivariate search tree, the 2-3-4 tree. Thank you.